First of all, we are going to explain what is the origin of the trigonometric identities. The term trigonometry comes from the Greek word trigonon, meaning triangle, and the Greek word metria, meaning measurement. The word trigonometry was later introduced by the German mathematician and astronomer Bartholomeus Pitiscus in the title of his work Trigonometria sive de solutione triangularum tractatus brevis et perspicuus, published in 1595 AC. The sine and cosine functions were developed in the context of astronomy, but the tangent and cotangent functions were derived from the practical measurements of heights and distances. So we are going to travel to the ancient era, where we find the first time that a trigonometric term appears. The first place we are going to talk about is Babylon. In this place, there was the Plimpton 322, which was created in the 1900s BC, in which some experts tell that this clay tablet contains a fragment from a proto-trigonometric table. Now we are going to talk about the Egyptian input to trigonometry. In this place, the Rhind mathematical papyrus was founded. It was created in the 1680 BC, and it contains 87 problems, from which problems 56 to 60 contain basic trigonometry problems. Now, if we go to Greece in 140 BC, we can find Hipparchus of Nicaea, who was a Greek astronomer, geographer, and mathematician. He is considered the founder of trigonometry. He developed trigonometry and constructed trigonometric tables, and he solved several problems of spherical trigonometry. With his solar and lunar theories and his trigonometry, he may have been the first to develop a reliable method to predict solar eclipses. As well as Hipparchus' table of chords, there were other trigonometric tables, such as the Ptolemy's table of chords and Almagest, which have the equivalence of several trigonometric identities and formulas, such as chord 2x plus chord 180x minus 2x equals 4r, which is equivalent to sine of x plus cosine of x equals 1. Now let's go to Arabia 830 AC. Al-Battani. Al-Battani was an Arab astronomer, astrologer, and mathematician. One of Al-Battani's best-known achievements in astronomy was the determination of the solar year. He discovered the reciprocal identities or functions of secant and cosecant, and produced the first table of cosecants for each degree from 1 degree to 90 degrees, as well as a number of trigonometrical relationships. Later on, in the 17th and 18th century in Europe, we found some mathematicians or physicists, such as Isaac Newton and James Stirling, who get into the discovery of the power series for sine and cosine, as well as Leonhard Euler, who was mostly responsible for establishing the analytic treatment of trigonometric functions in Europe. Now we'll be working on proving trigonometric identities. Here we have our first example. We need to prove the identity cotangent of x over cosecant of x equals cosine of x. It's usually a safe bet to start working on the side that appears to be more complicated, so we are going to work with the left side. Something that can be very useful in these exercises is converting everything to sine or cosine. Our first step will be searching what cotangent is equivalent to. As you see, here we have a picture of our quotient identities, in which it says that cotangent of the angle equals cosine of the angle over sine of the angle. So we are going to write cosine of x over sine of x in red. And now we are going to look for cosecant of x, which we are going to write in orange. As you see, in our reciprocal identities, cosecant of x equals 1 over sine of x. Now we have this huge division that we can solve with the sandwich rule, multiplying cosine by sine in the top and sine by 1 in the bottom. So here we have it, cosine of x by sine of x over 1 by sine of x. As you see, what we can do here is cancel the signs, and that will leave us with cosine of x. So we are proving our identity as we have cosine of x on both sides. This was a very easy example, so let's do another one. We need to prove that tangent of x over sine of x equals secant of x. Again, we are going to start on the left side, and we are expressing everything in terms of sine and cosine in order to simplify. So we will look for tangent of x in our trigonometric identities, and here we have the tangent of x equals sine of x over cosine of x, which we are going to write in yellow. And then we're just going to write sine of x as sine of x over 1, dividing sine of x over cosine of x. As you see, we have another huge division that we can solve using the sandwich rule. We need to multiply sine of x by 1 and put it on the top, and cosine of x by sine of x and put it on the bottom. So here it is, cosine of x by sine of x. Now what we can do here is eliminating the signs, and that will leave us with 1 over cosine of x. Now if we take a look on our reciprocal identities, here we have that secant of the angle equals 1 over cosine of the angle. So we can replace this with secant of x, and again we are proving our identity as we have secant of x on both sides. So we've been using reciprocal and quotient identities, but what we haven't used yet is Pythagorean identities. So let's do an example in which we'll need to use these identities. Here we have our third example, which is sine of x by cosine of x by tangent of x equals 1 minus squared cosine of x. I'm going to replace sine of x with sine of x over 1. Then cosine of x, I will replace it, or I'll just put 1 on the bottom as I did with sine. But with tangent of x, I'm going to replace it with sine over cosine, which we see in our quotient identities, and we are going to write it in light blue. Sine of x over cosine of x. So now that everything is in sine and cosine, we can multiply these three factors, and we'll get sine of x by cosine of x by sine of x over cosine of x. As you notice, what we can do here is cancel the cosines, and we'll have sine of x by sine of x, which equals squared sine of x. Now, if we take a look to our Pythagorean identities, we have that squared sine of the angle plus squared cosine of the angle equals 1, which means that squared sine of x equals 1 minus squared cosine of x, which we are writing on dark blue. So now we have 1 minus squared cosine of x on both sides, which proves our identities. So let's do our final example, which will be a little harder than the others. And here we have it. Our fourth example is cosecant squared of x by square tangent of x minus 1 equals square tangent of x. According to our Pythagorean identities, 1 plus squared cotangent of x equals squared cosecant of x. So we are going to replace squared cosecant of x with 1 plus squared cotangent of x. As you see, we're writing it with purple. Then we write the squared tangent of x minus 1. And what we can do now is multiply squared tangent of x by 1 plus squared cotangent of x. So 1 by squared tangent of x equals squared tangent of x. And squared cotangent of x by squared tangent of x equals squared cotangent of x by squared tangent of x. And of course, we write the minus 1. As you see, we still have a multiplication here. So what we're going to do now is we're going to replace the squared cotangent of x and the squared tangent of x with cosine and sine. Remember that cotangent of x equals cosine of x over sine of x, which means that square cotangent of x equals squared cosine of x over squared sine of x. Then remember that tangent of x equals sine of x over cosine of x. As you see, we're circling it right here, which means that square tangent of x is equal to square sine of x over square cosine of x. And again, don't forget to write the minus 1. So what we can do here is cancel the squared cosines of x and cancel the squared sines of x, which will equal to 1, which we're going to write it right here. 1. And now we write square tangent of x plus 1 minus 1, as it's pretty obvious that 1 minus 1 equals 0, so this equals to tangent squared of x. Again, we're proving our identities because we have the same thing on both sides. Square tangent of x equals squared tangent of x.